Hello everyone, my name is Negar and I'm a PhD student at University of Waterloo. Today I'm going to present predicting efficiency effectiveness trade-offs for retrieval strategy selection, and this is a work by me and my co-authors Nicole Yan and Charles Clark. A few years ago, state-of-the-art ranking stack would have consisted of a sparse bag-of-word representation-based scoring methods such as BM25, which is based on exact pair matching, and then the ranking stack would leverage from other rankers in other layers. But when contextualized pre-trained transformer model emerged, a new type of first-stage retriever were introduced to the community. In these new retrievers, the query and documents are mapped into low-dimensional dense vectors, and then some maximum inner product search methods are used to find the documents with highest similarity to the query. Some nearest neighbor search methods, such as FACE, support these dense retrievers and let us scan millions of candidates in milliseconds and use dense retrievers in practice. If you want to compare the sparse or like methods such as BM25 versus dense or BERT-based methods, we can say that dense retrievers are usually shows higher performance in terms of effectiveness compared to sparse retrievers, but also they are computationally more expensive and they are less efficient, and their query latency time is higher than sparse retrievers, which are super fast. And sparse retrievers, we can say that they are based on exact matching, but dense retrievers are usually based on semantic matching. Although dense retrievers outperform sparse retrievers in terms of effectiveness, there are still queries that sparse retrievers shows a better performance on them, and there is no single retrieval method that can definitely say that can definitely answer all the queries effectively and efficiently. There are also a third group of retrievers, which is hybrid retriever, and it combines sparse and dense retriever in the hope of gaining advantages of both. There are different hybrid retriever methods. For example, they interpolate the relevance score from each, or they use sparse retriever lexical information in the training process. In this work, our goal is to select appropriate retrieval strategy for individual queries. Given that we have sparse, dense, and hybrid retriever, we want to maintain and balance the relationship between effectiveness and efficiency and select the most appropriate retrieval strategy per query. To do so, we want to leverage and get the benefits from both. For some queries, we might use dense retriever because we want to avoid vocabulary mismatch. For some others, we might use sparse retriever because exact matching is necessary. But when both are desirable and when both sparse and dense retriever can answer the query, we prefer the retriever with lower cost, lower latency, which is sparse retriever. Generally speaking, we can say that we want to capitalize on the efficiency and parsimony of sparse retriever, and when both are possible, we prefer sparse over dense. So our approach includes training a classifier in a cross-encoder architecture with BERT embeddings, and the goal is to select the retriever that can answer the query the best. Our classifier obviously needs some labels, and we generate our labels based on the position of the first relevant retrieved document from sparse retriever. Basically, we are saying that if the first relevant retrieved document from sparse retriever is ranked among top T retrieved documents, a sparse retriever is capable of retrieving relevant information, and thus the proper retrieval strategy for this query is sparse. Otherwise, if there is no relevant retrieved item among top T retrieved documents, we need to go with dense retriever. We have a second classifier with similar labeling scheme, and here we decide between sparse and hybrid retriever. The only thing that I should note is that in hybrid retriever, we have the results from sparse and dense. So we first retrieve with sparse, and then based on the results, we can decide if we need to do the dense retriever as well or not. And here is our training architecture. We use bird embedding representation of the queries, and we feed the query tokens followed by special tokens into cross-encoder network. And then there is this linear classification layer with binary cross-entropy loss on top of the CLS token produced by transformer to reduce the dimensionality. And we need to get a scalar value, which indicates the probability for each class. We should note that in the hybrid, sparse versus hybrid architecture, we use query tokens as well as the tokens of first retrieved documents by sparse. And we leverage an extra piece of information in the similar architecture. We ran our experiment on MS Markov passage collection, which includes almost 8 million passages and more than 500,000 pairs of query and relevant judged passage. And we did our tests on small development set of MS Markov, which includes around 7,000 queries. We represent a group of sparse retrievers by the well-known BM25, and our dense retrievers with Anki, Repert, and Colbert, which are among state-of-the-art dense retrievers at the time. So here is the result of our using our retrieval strategy selection in terms of recall. Let's look at this figure. The x-axis in this figure indicates the dense or hybrid budget, and the y-axis represents the recall at 1,000. So here the dense, but let's first focus on the blue figure. Here the dense budget is 0. It means that we retrieve all the queries by sparse retriever and we get a recall of 0.86. If we jump to this point on the top right, we get the dense budget of 1, means that all the queries are retrieved with dense retriever, and we get a recall of 0.96. The dashed line here means that we randomly allocate some percentage of the query with sparse and the rest with dense. For example, here, when the dense budget is 0.4, meaning that 40% of queries are randomly retrieved with dense retriever and the rest with sparse retriever, we get a recall of 0.9. But when we intelligently allocate these groups of the queries with sparse retriever, with dense retriever, we increase this 0.9 recall to 0.94, meaning that if we intelligently select 40% of the queries to be retrieved with dense retriever, we can increase this recall. And then we have this similar graph for sparse versus hybrid retriever. But then there is an interesting gap here between when we go fully dense or fully hybrid. And this gap indicates that sparse retriever can complement dense retrievers, and there are queries that dense retrievers cannot retrieve relevant item and sparse retriever can help them. We replicated this experiment with with 3 different dense retrievers, Anki, Repert, and Colbert, and all of them showed similar performance. And this means that the type of dense retriever doesn't affect our conclusions, and our method is robust to the type of the dense retriever. And let's say we can select the appropriate retrieval strategy. How would this impact on query latency time? Here we have the reported query latency time for sparse retriever, which is 55 milliseconds, versus the reported query latency for Anki as the representative of dense retrievers for 103 milliseconds. If we go here on the right figure, we see the query latency versus recall. If we go fully sparse, we get the recall of around 0.86 with 55 milliseconds. And if we go fully dense, we get the recall of, let's say, almost 0.96 with the recall of 103 milliseconds. And in between, with our method, we get this nice Pareto frontier shift between the retrieval strategies. And when we vary the budget and when we have time or performance constraint, we can get our recall or our query latency time. For example, let's say we have the time constraint and our query latency time should be less than 80 milliseconds. Based on this frontier, we know that we can get a recall above 0.94 when the query latency time should be less than 80. To conclude, we showed that dense retrievers provide substantial performance improvement compared to sparse retriever, but they still miss some relevant items which can be surfaced by sparse retrievers. And in terms of efficiency versus effectiveness, we present that selecting the appropriate retrieval strategy can help dense retrievers to be used on only queries that are most likely to benefit from. And also we show that utilizing our proposed retrieval strategy selection helps achieving improved performance when there is resource or time constraints. Thank you everyone for watching this presentation. I would be happy to answer your questions, and you can ping me through email or on Twitter. Thanks.